Hey everyone, Mr. Evans here with your pre-recorded live lesson for Unit 7, Lesson 3, The Distribution of Traits.
So a lot of the concepts in this lesson is stuff that we have gone over before. Just like a lot of the other lessons, it kind of goes over the same thing more than once. But the one exception to that is Hardy-Weinberg equilibrium. Now, don't be scared by the funny name or the fact that there are letters in an equation in this. It's really kind of basic, even though it looks intimidating. So Hardy-Weinberg equilibrium are named after the two biologists who kind of came up with the idea. And it's the idea that a certain allele, meaning a certain characteristic, is steady through a population of organisms, meaning that the trait is not becoming more frequent or less frequent. Is just about everybody either has it or the presence of the trait isn't going up or down in the population. So for example, robins, the bird, robins, they're pretty much everywhere, and it's a pretty common example. Everyone knows what a robin looks like. It's the birds with the orange feathers on the breast. You see them in the morning picking at worms in the lawn. So that orange breast is a characteristic on robins. It's like their most definable thing. And that trait is steady in the robin population. Pretty much every robin has that. Generally speaking, the males are a little bit more brightly colored than the females, but it's constant. So for that particular trait, for orange feathers on the breast, that trait in the robin population is in equilibrium. And there are some conditions that have to be met for a population to be in Hardy-Weinberg equilibrium. And there's no species that will 100% meet all of these conditions, because there is no trait that is like 100% guaranteed to be steady throughout a population all the time. Things are always changing, things are in flux. So you are approaching things can like approach Hardy-Weinberg equilibrium, but they'll never actually get there. Something will never be 100% guaranteed steady, because things happen. Traits change, genes mutate as the generations roll on. Evolution's always happening. But 5 factors for perfect Hardy-Weinberg equilibrium have been established. Even though nothing will ever get to perfect equilibrium, these are the 5 things that have to theoretically be met for perfect equilibrium. The population cannot have mutations. Obviously, mutations happen all the time. That's not a 100% thing. So it's impossible for a population of animals to have 0 mutations like ever. This is like a theoretical idea. But the idea is, if there's mutations happening, if they are living in toxic waste, or I don't know, something happens that increases the mutation frequency, they are moving away from Hardy-Weinberg equilibrium. So that is perfect scenario number 1. No mutations, but that doesn't happen. So it's a theoretical thing. I kind of want to hammer that in. This is an idea that you try to approach, but you never actually reach. Number 2, there can be no gene flow. There's always gene flow, but you can have more or less gene flow. Like animals can migrate, certain members of the species of that population of animals can migrate in and out of an area. Maybe they get separated, stuff happens. But again, this whole thing right here, these 5 factors are theoretical things. This is what would, if there were perfect equilibrium, this is what you would have to have. But again, you never actually get there. There can be no selection, meaning that the survival pressures would have to be like very, very, very low. Plenty of food, free availability of mates, low predators. Mating must be random. Mating among the animal population is more random than it is among humans, but it's still not completely random, especially among birds. Male birds have to have the bright feathers and do these like exotic dances and sing bird song to try to attract a mate. And there's other behaviors all across the animal kingdom about having bright colorations or doing specific rituals or calls to try and attract a mate. So again, mating is not completely random in the animal kingdom, and the population size must be infinite, which obviously doesn't happen. There's no such thing as an infinite population. So I'm going to mention it once again. Hardy-Weinberg equilibrium is not something that is ever 100% met. No population can ever get to 100% equilibrium for like perfect and stable variation in frequency of traits throughout their population. But these 5 things represent what would have to happen for it to get there. These 5 things can never all actually happen, but maybe you can get to 85% equilibrium or 90% equilibrium. Or maybe it's really low. Maybe the genetic frequency characteristic population is going crazy for some reason and it's at like 20% equilibrium. So it's just an idea to understand how certain traits are moving through a population of animals. Now, if you're a biologist who studies robins or any other type of species, if that's your thing, then this is important to know. You need to know what traits are appearing or disappearing in the population of animals that you're studying. Are the traits for the birds changing because of human activity or climate change, or has an invasive species moved into an area? You know, if you're studying sparrows or robins for 40 years of your life, and 20 years in, you notice that the robin's orange feathers are starting to become more dull and more brown so they can blend into the canopy of the trees a little bit better, and you notice that, and you can see that they're moving away from equilibrium because of that change, there's got to be a reason why. Maybe some kind of new predator has moved into the area, or maybe there's been a mutation to an environmental factor. But this is something that a biologist is going to look at and know. All right, so let's go over the example here that they give you in the lesson. Here is our equation. Now, don't be nervous that there's P's and Q's in this equation. Got to mind your P's and Q's. The P's and Q's are just substitutes for numbers that a biologist would find while doing research in the field. So the P squared in this equation is the frequency of the heterozygous dominant genotype. So in the example of the robins, let's say that the orange breast is the dominant trait and tan breast feathers are a recessive trait. I don't even know if that's really a thing. I'm just using it as an example because it will work. So in this case, P squared would be heterozygous dominant genotype. Now you couldn't know if they were homozygous just by looking at them. You'd have to do further testing. I mean, you could look at a robin and say, okay, it has an orange breast, so it's either homozygous dominant or it's heterozygous, because in our example here, we're saying that A, the orange feathers, is dominant. But we could start there. So P squared is the frequency of robins that's homozygous dominant. Let's say we took a sample of 100 robins and we did all of our testing and we found out that 50 of them were homozygous dominant. That would mean that 0.5 of our sample size, 0.5, 50%, is homozygous dominant. And those numbers can only be done by counting and doing research. So we're just substituting P squared for an unknown that we'd have to do a little more research to find. This factor, 2pq, is the frequency of heterozygous genotype in the robin population. So it would have one allele for the orange feathers and one allele for the tan feathers. We're going to call tan recessive here in our example. So let's say we did all our testing and everything, and we found out that 30% of our robins are heterozygous. So that would be 0.3. Q squared is the frequency of homozygous recessive, little a, tan feathers. Now you could look at these robins, and if they have tan feathers on their chest, then you would know that they're homozygous recessive. And from our sample size, we looked here and we found out that 50% were homozygous dominant, 30% were heterozygous. So what's left? 20%'s left homozygous recessive. And you can verify that just by looking at them. For these other two here, you might have to do a little bit further testing. But in this equation, it's always going to add up to 1. You always have, if you're doing a sample size, your numbers are always going to add up to 100%. And this is assuming there's 3 possible genotypes for this gene. So this is like our simplest example. These are the only options here for this particular gene: homozygous dominant, heterozygous, or homozygous recessive. So in the perfect equation, it always adds up to 100%. It's very hard, if not impossible, to get perfect results in a field study like this, but that's the idea that we're shooting for. So why would you do this? Well, for one thing, again, like with any math equation, if you only have one unknown variable and there's an equal sign in it, if you know P, you can figure out Q. If you know Q, you can figure out P. So that is something that is useful if you are having trouble finding both variables in the population. Now, what would you use this for? If you're a biologist tracking these animals and you notice a shift in Hardy-Weinberg equilibrium, and you would plug that number into these math equations, that would give you a clue that something about that population is changing. The frequency of a certain trait is changing. So for the robin example, if you're a biologist and you got your numbers and you plug those in and you know the frequency of a gene in the robin population, and 5 years later you go out and you do the study again after they put a freeway through their habitat or something like that, or maybe like some people moved into the area, maybe they like built a neighborhood in that area or something, and all those people have cats, they have pet cats that they let outside. Maybe you would notice that some of the robin's feathers are not as brightly colored. You might notice the frequency of the tan allele increasing. Now, why would that be? Well, because if you're a cat and you see robin with bright orange feathers, it's easier to see. Robin's less camouflage, easier for the cat to catch. Tan feathers might give you a little bit more camouflage to hide from those cats. This is just an example I'm making up off the top of my head, but if you're a biologist looking at this stuff and you notice a shift in gene frequency, you could say that Hardy-Weinberg equilibrium had been disturbed, and you're seeing a trait spread throughout the population at a higher rate. And as a biologist, you would say to yourself, why is that happening? Further research is required. So I just wanted to go over Hardy-Weinberg equilibrium today, because that's like the weirdest thing in this lesson, and most of the other stuff has already been covered. But again, don't let the fact that there's an algebra equation in here freak you out. The P's and the Q's are just placeholders for numbers that would have to be found in the field through observation. And as those numbers change, you could notice that a trait is becoming more or less frequent in a given population of animals. So that's it for today. Thanks everyone for coming.